Let us begin our class. So today we are going to study students. Do you have any doubts in our previous topics? Okay, let us begin a new concept. CPU, Central Processing Unit. If you look at the syllabus, we have done microprogram control unit, control memory, address sequencing, microprogram example, design of control unit. Okay. Now we will start with central processing unit. So the first topic is general register organization. Central processing unit or CPU. So CPU, as you all know, CPU has three components: ALU, arithmetic and logic unit, CU, control unit, and registers. Look at this figure. This shows major components of CPU. This is control unit, which supervises the timing of the operations, and register set holds the intermediate results, and ALU, arithmetic logic unit, that performs the arithmetical and logical micro operations.
Hello, ma'am. Ma'am, we are unable to see the screen, ma'am.
Yes.
Ma'am,
Yes.
have you shared a PDF, ma'am? Like on the screen?
Which PDF?
You are explaining about CPU, right, ma'am?
Yes.
That PDF.
This is textbook.
Like you are explaining orally, ma'am.
Okay, you want to share, or you want this
Yes.
entire PDF file?
Like on daily, you are explaining by showing the figure and the concept, ma'am. Today
Yes.
you're only explaining, not sharing the PDF, so that's why I'm asking, ma'am.
But, okay. You are not able to look at PDF?
No, ma'am.
I am sharing PDF. Uh, I think others able to look at this figure? Yes, please respond. Give me response. Who is there? Srinivas? Are you able to look at figure?
Good morning, ma'am.
Good morning, Srinivas. Did you look at? Did you see the figure?
No, ma'am. Only audio will visible.
Okay. Now.
No, ma'am.
Now is, oh, okay, okay. I have not shared the screen. Right. Very good.
Okay,
See,
ma'am.
I forgot to share the screen. Okay. Now are you able to see the screen?
Yes, ma'am.
Oh, very good. So this is the figure of CPU. which has control unit, register set, and arithmetic and logic unit. So these three components of CPU are, connected. All the three are connected. What ALU does? Uh, First, what CU does? CU initiates timing signals to for registers and for this ALU for uh, to perform micro operations, that is uh, you know uh, driven by timing signals generated by control unit. And this ALU performs micro operations, and this register set stores the intermediate results. Okay, so let us look at journal register organization. Can anyone give me the names of
Ma'am, till now the screen is not coming in.
now, even now? But now I have shared it.
Yes, ma'am. We are able to see this.
You are able to see?
Yes, ma'am.
Yes, ma'am.
Srinivas, are you able to see? Please, all of you, uh, check your internet connections, our settings. I have shared the screen, and most of the students are able to see. Students, can anyone tell me what are the registers that we studied in our earlier chapters? Yes, quick, quick. Registers that we have looked at in our previous chapter. No one remembers? Yes, Ramakrishna, Sai Krishna, Saraswati, Yuta Nani. Who is Yuta Nani? No one remembers?
Madam,
Hmm? Tell me any register which we studied in our previous chapter. Please, quickly. No one remembers any register which we studied? Yes, Ramakrishna. Okay, I will only tell. We studied accumulator, program counter, address register, data register, instruction register, input register, output register, temporary register. These are the 8 registers that we studied in chapter 5. And in chapter 8, in this current chapter, we will study journal register organization. Those are specialized registers. Look at this journal register organization. In this, how many registers are there? Okay, this one, we have 7 different registers. Look at here: R1, R2, R3, R4, R5, R6, R7. These are 7 general purpose registers in a processor. All right. Next, you have ALU, which is also a component of a processor, arithmetic and logic unit. And these 7 registers are connected to ALU by means of multiplexer. and also you have an external input. So in total you have 8 inputs to this ALU. This is 1 plus 7 registers. So 7 plus 1, 8. This multiplexer has selection lines B and this selection line A, and this is 8 by 1 multiplexer. 1 2 3 4 5 6 7 8, total 8 inputs we have to this multiplexer, and there is one output coming out of this multiplexer, and there are 3 selection input lines which are named as cell A for this multiplexer. For this multiplexer there are 3 selection input lines known as cell B, selection input lines B. This multiplexer also takes 8 input lines, and there is a clock here to these registers, and you have a decoder, 3 by 8 decoder, which uh, also requires selection lines, 3 selection lines, because this decoder is 3 by 8. Actually this is not selection lines, it is like input, three inputs, and you get 8 outputs in a decoder. It is a 3 by 8 decoder, and the output of ALU goes to any one of these registers, R1 to R7. The output goes to any one of these registers based on the clock, based on which register is activated for that particular operation. This is your block diagram of journal register in processor, and you have a control word. What is a control word? A control word is a instruction sort of uh, thing which is stored in a memory. So you have OPR, operation, SCLD means this input to decoder, SCLB this input to multiplexer B, SCLA this input to multiplexer A. Okay, so suppose if you have to perform an operation R1 equal to R1 plus R2. What is this R1 equal to R1 plus R2? This is like you are adding the contents of R1 with the contents of adding the contents of R2 with the contents of R3, and storing the sum or the result into R1. These are 3 registers, general purpose registers. Now look at here, what happens is multiplexer A, selector, cell A, it places the contents of R2 into bus A, and mux B, uh, which is driven by cell B, it places the contents of R3 into bus B, and ALU performs OPR, which is plus, and the result goes into R1 because of this decoder destination selector cell D. So it transfers the contents of output bus into R1. So again let us go through this. This is bus A, this is bus B. The output of mux is known as bus here. Okay, so you have bus A, bus B, and you have this decoder output line, and then this control word contains plus in place of OPR, contains for cell A uh, what it has to choose. It has to choose cell A R2. See, look at here R2. Look at here R2 contents. Okay, here cell A. Then next you see here R3. Second operand is R3. So R3 is given to cell B, mux B, and placed on this bus. On this bus R2 is placed, on this bus R3 is placed, and then ALU performs the operation. Which operation? This OPR is plus, and then the result, the sum of R2 and R3 is stored in R1 because of this R1 is equal to, this is transfer operator, it is like equal to, so R1 equal to, from here R2, from here R3, both plus, the result goes to R1. And how it is decided that the result has to go to R1? Because of this decoder cell D. Okay, I hope that it is clear to you. Okay, here this is this nothing but encoding of the register selection. How do you select register 000 means it is input, no register. Where is the input? If you remember, this is the input. If you put 000, then it is input. If you put 001, it is R1. If you put 010, it is R2. 011 is R3. These are the binary codes. When used in this control word, when they are used in this control word, it is determined which of these should be selected. Yes, anyone is having any doubt? And because OPR, the length of OPR is 5 bits. Length of input or register means, again let me show you this. Length of cell A 3 bits, cell B 3 bits, cell D 3 bits. Length of OPR 5 bits. Okay. So if you look at here, this is the length of cell A, cell B, cell D. Cell A, cell B, cell D. So 3 bits are used to determine which register, and 5 bits are used to uh, specify the opcode, operation code. If all 5 zeros, it is like transfer A. If 4 zeros followed by 1, it is increment A. These are the operation codes, binary codes for these operations. Now, can anyone quickly tell me what will be the values for cell A, cell B, cell D and OPR? Look at these codes. Look at these codes and tell me what will be the value of cell A, and also look at this. Look at this and look at this and look at this and tell me what will be the what are the codes for that control word. Can anyone quickly tell me? Rajeshwari, Kirti, Amarinder, Saraswati, Yudha, Sai Krishna, Pavani. No one can tell me?
Ma'am, can you ask again the same question?
Again? Okay,
Yes,
who is this? First tell me what is your name?
I'm Saraswati, ma'am.
Saraswati. Okay. Look at this, Saraswati.
Okay.
What we are trying to do is, here this is our architecture, block diagram. Okay, block diagram of general purpose registers. This is our instruction format. This is our instruction format. In this you see cell A is there, cell B is there, cell D is there, OPR is there. Okay. Now what I want you to tell me is, this operation is there, no? R1 is equal to R2 plus R3. This has got specific codes, binary codes. Look at here. These are the codes. For if you want to choose R1 for cell A, you have to give 001. If you have to choose R2, then you have to use 010. And if you have to perform these micro operations, ALU operations, then you have to, binary codes for these operations are these. So what operation we are performing in that example, that is plus R2 plus R3. So what will be the code? It will be 00010. If you perform subtract, the code will be 00101. So what I want you to tell me is, just try to place these codes, these register codes and operation codes for this operation in this format. Can anyone do that? What will be the value of cell A? What will be the value of cell B? What will be the value of cell D and OPR? For this particular operation using these particular codes. Saraswati, can you tell me now?
Like,
Please try. If you try, you will learn.
yes, ma'am. For R1, we are adding R2 and R3, ma'am.
Yes. And putting the result in R1.
Yes, ma'am.
It is like R1 is equals to R2 plus R3.
R3.
Now tell me.
For cell A, cell B, and cell D, and
Yes.
opcode.
Yes. Yes. I want that. What is cell A? What is codes?
Like, we should add a cell A, cell B, cell D, ma'am.
No, no.
Then how can we get, ma'am?
How can we get? We can get by putting those codes 0000001 in this format. Here, look at this format. Are you able to look at this control word?
Yes, ma'am.
In this format, you put those codes. What is cell A?
Cell A.
Is R2.
R2.
Cell B is R3.
Yes, ma'am.
OPR is A plus B plus.
Yes,
And cell D is R1. Now you tell me.
R2 001 cell A.
Cell A is
010, ma'am.
010. Very good.
And R3 is 011.
Very good.
And cell D is R4, right, ma'am? 100.
Cell D is
No, A plus B, ma'am. Sorry.
no, cell D is R1.
Okay. Storing the R1 plus
Yes,
R2 in the R1 plus. Yes,
cell
ma'am.
D.
That is 001, ma'am.
Very good. Now what is the operation?
Operation is addition. That is 00010, ma'am.
Very good. So I hope that now everybody is clear. Look at here. It is like this. Now this for subtraction R2 for R cell A is R2, so 010. Cell B is R3, so 011. Cell D is R1, so 001. And here OPR is minus, not plus. In this example, this is a different example, another example. So subtraction is 00101. So I hope that it is clear to all of you. Next, coming to the next topic, that is stack organization. Okay. Now quickly tell me what is a stack. You all know it.
La Last in, first out, ma'am.
Stack is a last in first out
First out.
structure.
Yes, ma'am.
Last in first out structure. So what happens in stack is that whatever element you place in the stack, um, it goes into the bottom, and whatever item you place next, it is like a stack, means layers. So the last element which is inserted in the stack is the first one which is accessed through stack. So this stack has several uses in a computer system. Okay, we will look at what are the different uses of stack in a computer system. The first use is it is essentially a memory unit. Uh, you have a part of memory unit which functions as a stack. Whenever you make calls to functions, whenever you write a program, suppose you have 10 functions to be called. You have your main function and you have 10 other different functions. Okay, so what happens in memory is the area of memory which is called as a stack is used by the system to call the functions. So what happens is whenever you call a function, it is placed in the stack, and all the local variables of that function are also placed in the stack. And then whenever you come out of return, whenever you return from the function, it is removed from the stack. And if suppose you call another function, then again it is placed in the stack. Likewise, you go on placing the functions, and once they are done, you just pop them out of the stack. That stack is nothing but in hardware within memory. You follow that procedure of last in and first out. Um, Also, stack is very useful for um, arithmetic expression evaluation. Okay, so first let us look at how it is used in this memory. So this is a block diagram of a 64 word stack in memory. You have stack pointer, you have two flip-flops that keep track of the status of stack, whether it is full or empty, and these are the addresses of the stack. Please remember, here we are talking about the area of memory in hardware which is functioning as a stack. Every data structure which you studied in the subject of data structure has real world applications or real time applications in computer system. You study stack and then you write a simple stack program in a programming language, and then you pop push elements and pop elements, and that's it. But that is not the scenario. It is quite different. How is it different? That simple stack, whatever you have implemented in a simple program, has got tremendous applications. Whenever you write the code for operating system, you use a stack. When you write code for DBMS, in very complicated and complex systems, also these stacks, queues, these data structures play very important role. Data structure is a really uh, significant subject in computer science. It has got uh, enormous um applications. So for now it all seems very abstract. But then when you become developer in your future, when you write software programs, when you write complicated application, in that it gives you a lot of flexibility and also efficiency, if you know the particular data structure. So when you are studying data structure, try to search the real time applications of every data structure. Then the essence of learning data structure uh, will be achieved, and you will be surprised to know the several applications of data structure, and you will be amazed. It will be like uh, a different feeling altogether to know the real world applications of all the data structures. So I urge you all to look up the Google to search for all applications. Here in this computer organization subject, we are studying a stack application. Here we don't pay focus on what is a stack, how it is implemented. Rather, we focus on its application. How is it implemented and what is the application of it? So I hope that it is clear. It gives you the real big picture of the data structure subject. Next, uh, in this you have a full, you have empty. Those are the flip-flops which tracks the status of stack, uh, whether it is full or empty. And there are 64 address locations, 0 to 63, and the stack pointer is like a top. You have top in a stack, that is a stack pointer. And whenever you create a stack, you give the size of an array, int a of 10. So what is a of 10? Number of locations in a stack. So here you have 64, and their addresses are from 0 to 63. Next, what do you do when you perform some operations on stack? First you increment the stack pointer, and then you memory of SP, because here a stack is nothing but an area of memory. when you refer to stack, you have to say m of the stack pointer, which is here. uh, when you create an array int a of 10 and then you say a of top, if you remember stack program, you say a of top or a of t, and you say t plus plus or t equal to t plus 1. So same thing we are doing here also. M of sp stack pointer, which is like a top, and you are transferring the contents of data register into stack, which is a memory. And here you are checking if sp equal to 0, then full equal to 1. What do you say if you check if stack is full? And mark the stack not empty, and you are marking here the stack to be not empty. So here what are you doing? You are reading from stack pointer. Memory means stack. M of sp means it is like a of t, array of top, because here stack is memory. You are getting it is like pop operation. You are reading from stack into dr, and then what are you doing? You are decrementing the stack pointer, and you are checking if the stack is empty, and if it is empty you are initializing empty to 1, and you are marking full to be 0, means if it is not full, it is empty. Okay, this is computer memory, divided into different units. This is our program. This is the area where we are storing the programs, means the instructions. Program is nothing but the sequence of instructions. And this is the area where you are storing the data or the operands. And this is the area which is called as a stack, which will function as last in first out. And this is the stack pointer, and this is the entire stack starting with 400123000. These are the addresses of stack. So this is a computer memory. This is a computer memory divided into different areas: program, data, stack. And this is your data register. What is a data register? It is a processor register which will hold the operand. Next, what you have to do, you have when you are transferring the contents of dr into stack, and here you are transferring the stack content into dr. So this is like reading from the stack, and this is writing to the stack. This is writing to the stack, and this is reading from the stack. Okay, another application. This is in hardware. This is a stack implemented in hardware, in memory. It turns out that stack has a application in software, in evaluation of arithmetic expression. Okay, so let us look at how a arithmetic expression is evaluated. Suppose you write a program. To do this: a into b plus c into d. For human being, having operator in between operands is relatively easy to comprehend and evaluate. Whereas for computer system, this type of notation is quite difficult to evaluate and comprehend and interpret. So what you have to do is, in the sense the compiler does that. When you write a program to perform this, compiler has to execute these instructions, and then what compiler does is it converts this infix notation of the arithmetic expression into prefix or postfix. Okay, it depends. A Polish mathematician, Lukasiewicz, showed that arithmetic expressions can be represented in prefix form. So this representation is also referred to as Polish notation, because the mathematician who has showed how to represent an expression using prefix notation is from Poland, I think. From Poland, people are called as Polish, no? So that's why it is called as a Polish notation. Okay, so this Polish notation is like putting the operator before the operands. Okay, then what will be the postfix notation called as? It is called as reverse Polish notation. If prefix is called as a Polish notation, then postfix will be called as reverse Polish notation, RPN. And what happens in reverse Polish notation? The operators appear, operator appears after the operands. First you have operand, then you have operator. So how do you convert this infix notation into reverse Polish notation? I think you know the procedure. What happens is, what do you do here? First you write the operands. What are the operands? What are the operands here? A, this is first operand. And if you put operator here, this is in between operands. So what you have to do, we are going for reverse Polish notation. Reverse Polish notation means in reverse Polish notation, what happens is, you first put the operands. So A, B, and what is the operator? Star, which is a multiplication operator. Okay, and then essentially what happens here is that you have to consider the priorities also. Priorities of the operators are also important. Here in this expression, A into B is evaluated first, then C into D is evaluated means at the same time. A into B, C into D, both are evaluated. Then the result of A into B is added to the result of C into D, means the product of AB is added with the product of CD. So AB star you do first, then you do CD star. Okay, then what do you do? Then
Addition.
addition. So first you get this product, then you get this product. So this is first operand. This is the first operand, this is the second operand, and this plus is the operator. For this operator, this is the first operand, this is the second operand, and this is the operator. This is the first operand, second operand, operator, and this whole expression is the first operand, this is the second operand, and this is the operator. Okay, this is reverse Polish notation. I hope it is clear, you all have understood it. Okay, then look at here. We got the same thing, no? Same. Okay, then we will look at how this is used for evaluation of arithmetic. See, look at here, there are some expressions given. Please try to convert them from infix to postfix and prefix, means infix to reverse Polish notation and Polish notation. It will be a sort of practice for you. I am giving you an exercise today. Please look at all those expressions. Now we will look at how stack is used to evaluate an arithmetic expression using reverse Polish notation. So this is our expression. 3 into 4 plus 5 into 6. You have to perform first multiplication of 3 and 4 and multiplication of 5 and 6, and then add both the products, and the conversion of that into a reverse Polish notation is done here. Okay, so it is expressed in that. Now look at how a stack is used for that. First, initially stack is empty. When a stack is empty, a stack pointer will be pointing to the 0th location, and then you insert 3. Okay, so please remember this reverse Polish notation, because we are using this reverse Polish notation to evaluate the expression in a stack, using a stack. Look at here, first step, this is first step. You are inserting or push, you are performing a push of 3, so 3 is added, and now you perform push of 4, because our expression is 3 4 into 5, this is reverse Polish notation, 6 into plus, this is our expression. So first you are choosing this, then you are choosing 4, because the next element is 4. Now stack pointer is incremented and 4 is added. What happens is, whenever it encounters an operator, what it does is it pops the last 2 elements, it's like first 2 elements in the stack with respect to the stack pointer. So first 2 elements are popped of stack, and this operation, whatever operator it has encountered, that operation is performed on these 2 values which have been popped from the stack, and then the result is, you get some result, right? Then that result is pushed into the stack. So whenever it encounters operand, it performs push operation. Whenever it encounters operator, it performs pop operation. So 3 is operand push, 4 is operand push, asterisk is operator pop. Pop 2 elements. Pop 2 elements, perform that operation, and push the result into the stack. So you got here 12. Okay, when it encounters asterisk. Then comes 5. 5 means operand. Operand means push. 6. 6 is also an operand. Operand means push. Asterisk. Asterisk is operator. Operator means pop. Two elements. So the first element in the stack to be popped is 6. 6, which is the last one to be pushed. Okay, but as per this stack pointer, this is the first. So this one is popped. This one is popped. And then stack pointer is decremented. After pop operation, stack is decremented. So after decrementing, stack pointer will point to 5. 5 is pop. Okay, and then perform multiplication. So 5 times 6 is 30. Now the product 30 is pushed into the stack. Going further, it encounters plus. Plus means operator. Operator means pop. Pop 30, pop 12, and perform plus. Sum of 30 and 12. Then what do you get? 42. So the result is pushed into the stack. Now after plus there is nothing. The expression has ended. There is nothing to do. So it pops the one and only element in the stack and gives that as the result to the user. So the result 42 is given to the user. Did you all understand, students? Any doubt?
Yes, ma'am.
Please ask. Okay, students. So I hope today's class is clear to you all. All of you might have understood. Please go through. I urge you, students, now only open the book and read the entire two topics. Tomorrow's class we will study the next topic, which is, what is the next topic? Instruction formats, and possibly, if time permits, addressing modes. 8.4, 8.5 are the topics of tomorrow's class. I urge you all to study 8.1, 8.2, and also tomorrow's topic. Okay, students, bye. Take care.